Okay, so we'll start. So hi everyone, I'm Amnan. Today we'll talk about multi-view geometry and optimization, and specifically on bundle adjustment. More specifically, we will have some recap about what we have done in the course until now. We will discuss some multi-view reconstruction. We will talk about bundle adjustment. Then we will continue the optimization principles that you discussed with Meirav last week. We'll talk about least square optimization and nonlinear least square, and that's it. So the structure for motion problem you already should be familiar with. So actually we have so the problem is given the 2D projection of a 3D scene and the motion of the camera, we want to reconstruct the camera matrices and the 3D points. So where X, capital X is the 3D point in the real world, PI is the camera matrices of the eye camera, and lowercase x is the projection of the 3D point to the eye camera. So until now in the course, you have seen several cases and you learn how to reconstruct these cases. So the first case you've seen is the camera resectioning. We'll do a bit recap about it. So in the camera resectioning, you're given a single image in a local coordinates. And somehow you have 3D and 3D to 2D correspondences. You know what is the point in the world and what is its 2D projection. So the goal is to estimate the camera matrices using the correspondences 3D to 2D. So you have seen many algorithms to do that. One of them is the DLT. And there are several other algorithms. So this is actually the simplest case that there is in structure for motion. So the second case, which is a bit harder, is called triangulation. You've seen this in Yoni's lecture. Here we assume that n larger than 2. That we have more than 2 views, and we assume we have 2D correspondences between the views and the camera matrices, which you got from somewhere. So the goal in this case is given the n corresponding point xi, given the projection of the 3D point and the camera matrices. The goal is to estimate the 3D point, which is capital X. And actually, this can be done by solving the convex problem. Since capital X is given, and excuse me, since P is given and lowercase x is given, this problem is convex and there is a closed form solution. So this is the second case. And the last case you've seen in the course is a 2-view reconstruction. And actually you will see in a few lectures the multi-view case. But for 2-view reconstruction or multi-view reconstruction, we assume that we have more than 2 views. That we are getting more than 2 views, and we are given correspondences between the frames, between every 2 images, And the goal is, given these correspondences, to estimate the camera matrices P1 up to Pn and the 3D point x1 up to xk. So actually, the method you should be familiar until this point in the course is how to do two views, where you can take the fundamental or the essential metrics, you get the camera matrices, then you do triangulation and get the 3D point, and you get an initial reconstruction. For n larger than 2, you will see in future lectures, and we will discuss a bit about it today. So the question is, why shouldn't we stop here? So you've seen that we can do a full reconstruction given only the correspondences. We can get the motion parameters, which are the camera matrices, and we can get the structure. So the question is, why don't stop here? So the truth is that essential or fundamental matrices are suboptimal, which means that they don't give always the best solution. They give good initial guess, but usually it's not enough to get an accurate reconstruction. The second reason is that the essential or the fundamental matrices are two-step solutions, which means that you get the camera matrices, then you triangulate the points. So you first solve the camera parameters and then the structure. So maybe if we could solve them together, we will be able to achieve a better solution. And everything I told you until now, the problem is even harder when you have more than two views. Because actually the fact is that we know only how to deal with two views. We know how to solve two views, but when we have more than two views, we need to propagate information from two views to three or more views, which is actually harder. And I told you this in hand waving, but you will see exactly the problem in the multi-view lecture. And the last reason why we shouldn't stop here is because under some conditions, under some assumptions, actually we have an optimal solution, which called bundle adjustment, which is what we will talk about today. So to give you another motivation for the bundle adjustment, so why we should talk about bundle adjustment. So here are results from a paper from our group. And you can see the accuracy of the position of we actually did a reconstruction of the scene. In this column, you can see the number of cameras. And X bar is the mean error in the translation and the position in meters, and X tilde is the median error. You have the same quantities with a subscript BA, which means that it's the same quantity after bundle adjustment. So as you can see, the bundle adjustment improves by a large factor of between 2 times, and I think there are also 5 times improvements. So actually the bundle adjustment that you will see in a minute what it is very important for every structure for motion pipeline, and actually no matter what your application, you will have to do a bundle adjustment in order to get accurate enough solution. So I hope I gave enough motivation. So let's talk about a bit the problem formulation. So everything here should be you should be familiar with. So we are given an image projections of a 3D point xj into the ith camera. So we denote it by lowercase xij. And we assume that the observation are corrupted by Gaussian noise, which is like kind of standard assumption. You can argue with this assumption, but actually it's only necessary theoretically. It's not necessary practically. So actually you have the projection here. Here you have the projection of the 3D point using the camera matrices, using the camera matrix to the image plane, and you add it a Gaussian noise. So one quantity that is important for us will be the reprojection error, which you already seen in Meirav's class, which actually measures, given a 3D point, a camera matrix, and a 2D point, it measures the projection of the distance of the projection of the 3D point to the 2D point. So actually, as you can see, this is the formula for the reprojection error, which is the Euclidean distance. And to get some intuition, you have a point in the world, which is capital X. You project it to the image plane using the camera matrix, and you measure the distance between where you thought X should be, which is a lowercase x, and the capital X. So this is the reprojection error, and we will use it quite a lot in this lecture. So actually, it turns out that under the assumption that we made about the projection that we corrupted by a Gaussian noise, the configuration that maximizes the likelihood, and you will prove it in your next exercise, is actually to minimize the reprojection error, the sum of reprojection error. And it's worth mentioning that in this sum, we sum over all the 3D points. We have a scene with a lot of 3D points, a lot of 2D correspondences, and maybe a lot of cameras, depending on how many frames do we have. And in this minimization problem, we sum over all the 3D point xj, all the camera matrices pi, and all the 2D correspondences xij. Yeah. And the optimization variable, what we are trying to minimize, is over the camera matrices and the 3D points, which is exactly what we do. So a bit about the problem of bundle adjustment. So this is the objective, and actually, what is the problem in this? What is the challenges in this objective? So first is very nonlinear. In general, what we know to solve, let's say, efficiently, are convex problem. We would prefer a linear objective inside the convex function, and then we have, as Meirav told you, we have a closed form solution for linearly squared. But this term is this objective is not linear, and it's also not convex. So to get a bit intuition why it's not convex, it's because we divide here by our optimization variables, And actually, we multiply two optimization variables, which in general is also not convex. So because of the two reasons above, there is no closed form solution for this optimization problem. And if it's not enough troubles, so this optimization can become extremely large with a lot of parameters. Just to get some intuition for that. So if we have m 3D points and n cameras, so in the uncalibrated case, we'll have 3m variables for the 3D point and 11n variables for the camera matrices. And as you know, for the calibrated case, the camera matrix has less parameters, so we'll get 6n, but it's extremely large. Like, let's see an example. I think you saw this animation in the beginning of the course. So this is an example from our paper, and actually it's something that we reconstructed. So we have here 529 cameras, which sums up in the calibrated case. It's calibrated. You see the structure is aligned. So it sums up to 3,174 variables for the camera matrices. And in the structure, there are 274K points, which sums up to 822K variables. So if we sum both of them together, it's more than 800K variables, which is a lot. If you think in any, like maybe today in the deep learning era, it's not that much, but it's still a huge optimization problem. Another example why we want to solve it efficiently. So let's say we have some robot or a car that drive in a road, and we get a frames like every second or every few seconds or whatever. And let's say we want to locate the cameras, to build a structure and to get the location of the cameras. So actually, we will need to do the structure for motion pipeline, which includes bundle adjustment. We will usually need to do it in real-time speed, which means that we will want to be able to solve the bundle adjustment very fast. So this is another challenge in the bundle adjustment objective. So a few more words before we start with how to solve this. So it's not the bundle adjustment. Is not a direct solver for the structure for motion problem. We will see that because it's not convex, actually it requires a very good initialization. So we cannot throw everything into this objective and solve it. We need to begin with the initial solution, and it's also very sensitive to this solution. And it's called the bundle adjustment because the bundle of the viewing rays is locally adjusted to reduce the reprojection error. So if you wonder why it's called like this. All right, so actually now we will talk about a bit how to solve this optimization problem where we have many cameras. Here we show 3 cameras and many 3D points. So we'll discuss how to optimize this nonlinear least square problem. So the first step is actually to get a good initialization, because we discussed that the problem is not convex. In non-convex problem, in general, we cannot guarantee convergence to global minima. So actually, our final solution of the objective will be very dependent on the initialization. If our initialization will be bad, like here, we'll stuck in a bad local minima, and if we will have a good initialization, we will maybe converge to the global minima of the problem. So the first step is how to generate the initialization. As you've seen in Yoni's lecture, actually, for two views, there are not a lot of options. So we can get the camera matrices from the fundamental or the essential matrix. Then we triangulate the 3D point from the 2D correspondences. And actually, in this way, we generate an initial guess to the camera matrices PI, to the two camera matrices, and for the 3D point. And we can start to optimize. For more than two views, we need to use some more sophisticated techniques. So we will discuss it in future lectures, but just to give you some hint where we use this bundle adjustment. So when we have a lot of cameras, a very common solution is to solve the structure for motion problem sequentially. And what does it mean? It means that we start with a small number of views, with let's say 2 views, and sequentially means that in every iteration we add one more or several more views to the scene. So everyone hear me well? Yes. Question until now, by the way. All right. So sequential means that we add view by view until we get all the structure and all the motion, all the camera matrices. So an example for such algorithm is to start with estimate P1 and P2 from the, let's say, fundamental matrix. It can work with the essential as well. Then we can have 3D points using triangulation, as we discussed. And now for each additional view, we actually we calibrate the new view. We estimate the projection matrix, the camera matrices, using the 3D point and the correspondences of the 2D projections. Actually, you've seen that you can do camera resectioning, right? Because we have 2D correspondences between the new frame and the other frames. So we know what is the 3D corresponding point. So we have 3D to 2D correspondences, and we can solve using resectioning the camera matrices. Then we extend the structure. We compute the new 3D point from the point matches that we have. Actually, we do a triangulation for our new points. And then we refine all the points that we already have. Now we have a new camera. So probably the solution we get with more cameras, like if we do triangulation with 3 cameras, we can assume that it will be more accurate than only 2 cameras. So we re-triangulate all the points. So we have actually in this stage we have the structure and the motion for all the 3 views, or wherever we got in the sequence. And now that we have this initial guess, we do bundle adjustment. And actually, we can change the algorithm. Usually in practice, what we will do, so for every additional view, or every few additional views, we will do bundle adjustment from the beginning. Actually, so we'll solve the bundle adjustment problem for any new view that we add. This usually what we'll do in practice. In this specific algorithm, we can do the bundle adjustment at the end. So we discussed how to solve the problem for the initialization, which is the first step. And now we assume we have a good initialization. So let's see how we solve the optimization problem. So a few words about this optimization problem. So actually, this optimization problem is called the square problem. So in the case of bundle adjustment, we have a non-linear least square. In Meirav's lecture, you saw a linear least square. And in this case, as we discussed, our least square is not linear. So we don't have a closed form solution. So what we can only do is to look for optimization problem that only look for a stationary point, which means we cannot hope for a global minima. We can hope only for a local minima, but given that we have a good initialization, we can hope that this will be enough. So in contrast to general optimization problem, the least square problem have a very special structure that we will discuss in a few lectures. We will discuss in a few slides, sorry. And this structure can be used in order to solve it efficiently. Another property of the bundle adjustment is that the Jacobian, the first derivative of the objective, we'll define it also in a few slides, is very sparse. And this is because we have a lot of parameters, right? In this, we've seen that we have, let's say in the projective case, 3 times the 3D point plus 11 times the camera, in the number of cameras. But actually, in each of these terms, we have only a constant number of variables, right? We have here only 1 point, 1 3D point, and only 1 camera matrix. So we will try to take advantage of this sparsity. All right. So now we go into how to optimize the objective. So yes.
I have a question. If we start the initialization by solving the previous problem, so isn't the entire solution going to be slower by definition?
In general, yes, because the entire solution you need to edit the time that you take to do the initialization, right? So of course it will be slower, but otherwise you cannot solve it. Like without a good initialization, if you just throw all the parameters into the optimization problem, you won't get any. You will get like garbage. it's not because the objective is so non-convex. If you will start with some random guess, so most probably we'll get into some dead local minima.
Okay, thanks.
Yeah. So actually, I didn't mention it before, but I think that most of the works in structure for motion is actually just to get a good guess for the bundle adjustment. Like I think 90%. I wouldn't say a number, but a lot of works like our work or any other works is just to get a good guess for the bundle adjustment problem. And the like quality of the initial guess is very correlated with the quality of the minima of the bundle adjustment. All right, so in the last lecture you discussed with me, Rav, a bit about a general optimization problem, and you have seen line search methods, and specifically we discussed the steepest descent method or gradient descent or whatever. So in the line search method, actually the scheme is very straightforward. It's an iterative method where we start with some x0, and we want to generate a minimizing sequence by just updating our x by some direction p, and p and some scale of this direction alpha k, that will actually lead to a decrease of the objective of the function that we want to minimize. Like in each iteration, we decrease the value of the function. So this strategy actually can be divided into two separate ideas. The first two steps, let's say, the first step is to choose the descent direction, which is pk, and the second step is to choose the scale of this direction. So actually, you have seen how to choose the scale, and you have seen actually also how to choose the direction in some cases. But in this lecture, we will see a few other methods to solve this direction, to choose a good direction. And in general, what we'll see today is second order methods, which means that we will use second order information of the function. And specifically, we will discuss the Newton method, which is the most basic idea for these methods. Then we will discuss the Gauss-Newton, which is an improvement of the Newton method. And then we will discuss Leverber-Marquette, which is an improvement of the Gauss-Newton. And actually, at the end, what we use for the bundle adjustment is the Leverber-Marquette algorithm, but we need all the way in order to understand why does it work. So we'll begin by the Newton method, which is, as I mentioned, is a second order method. So by second order, it means that we take the Taylor approximation up to second order. Last week you've seen that we can take only the first order approximation, but in this lecture we'll see what happens when you take the second order, like higher order approximation of the function. And actually our goal, after we use the second order, the goal here is to minimize the approximation over the direction. So actually we can take, at each step we can take a derivative with respect to this direction in order, we have an objective, a quadratic objective, right? So we can take a derivative of this objective and solve it. And if we take a derivative of this, so we get that the Hessian of the function, we discussed about function from Rn to Rn, but in general you can think also for the one dimension if you like struggling to get derivative of this. And if you want to see more, you can go to the metrics cookbook. There is like a lot of formulas for such derivatives. So actually, if we take derivative of the objective with respect to p, we get this equation that the Hessian of the function at the current point times p plus the gradient equal to 0. So actually, if we assume that the Hessian of the function is strictly greater than 0, which means that it's strictly positive definite, we can invert this matrix and get a closed form solution for the direction, right? For each iteration, we can get a direction by just inverting, by solving this linear equation, right? So this is called the Newton method. This direction, the way of choosing this direction is called the Newton methods. And so so I told you how to choose the direction. So the next thing we want to do is to verify that this is actually a decent direction, right? Because we can, if it's not a decent direction, so it doesn't work. It doesn't worth anything. So I remind you that P is a decent direction of f at point x if the inner product between the direction and the gradient of f is smaller than 0. So to get intuition about it, so you probably learned in some calculus lessons that the gradient is perpendicular to the level set of the function, right? So if you can think about it, maybe I'll draw. This is the direction of the gradient, right? And if I'm perpendicular to the gradient, it means that I'm on the level set, right? So if this thing is equal to 0, it means that I'm on a level set. If this thing is smaller than 0, it means that I'm in a descent direction, right? It means that I'm going here in this direction. And if this is positive, it means that I'm going upwards. So this is about intuition, why we want to require that, why like this direction, meaning that the inner product with the gradient is smaller than 0. So let's verify that this is the case for the Newton direction. It's very simple. It's actually, we take an inner product of the direction of the gradient. We just put inside our definition of the direction, and we get this quantity, which actually is smaller than 0 by our assumption that the Haitian is positive definite. An equivalent definition of positive definite is that for any vector that we will multiply from both sides, we will get that this thing is larger than 0. So so we got that our inner product with the gradient is smaller than 0, which means that we have a descent direction.
What is the difference in performance between this method, Newton method, with this direction to the simple gradient descent?
Good question. This is the next slide. So actually, in general, under some assumption, in general, all these line search methods might happen that it's take a lot of time. Like you can find the counter example for each method to take a lot of time to converge. But under some assumption, gradient descent converges linearly, and second order methods in general converge quadratically. Like when I say linear and quadratically, like the error between the k step and the k plus 1 step decrease in quadratic, like in linear rate or in quadratic.
So actually, we might want to do the same in neural networks, but because we have too much parameters, so we cannot do like second order computations, right?
Yeah, exactly. So,
but also here you have like 800,000 of parameters, so it's not too expensive.
Yeah, it's too expensive. And we will see like how we can do more efficient. So actually you are right, yeah. This is exactly the problem in deep learning and in our case as well. So the Haitian is of size of number of parameters times number of parameters, right? So if we have around 1 million parameters, so we will get million by million metrics. So there is two problems with doing like second methods in order to optimize it. The first is to compute this million by million metrics, and the second is to invert it, which I think it's impossible. Or
and even to store it as well as
yeah, and to store it as well. Yeah.
Store, invert, yeah. If you can neglect calculating second order derivative, it's better. Although most of the time second order methods are much better than the gradient descent, due to what Amen said, that in the neighborhood of the solution, the convergence is quadratically and not linear, and this is very important.
But you're right, it is a challenge, and actually the next two methods that we will see aim to solve this this problem that that actually it's not feasible to solve this this problem. But I show you the Newton method first because it's important for in general for optimization, and second because it's the basics for the other methods. So so we need to get some intuition. So about the convergence rate, as you asked, so here is an example of this function, which is not quadratic. Someone knows why we didn't take a quadratic function?
If you took a quadratic function, Newton would converge in a single step, right?
Yeah, exactly. Everyone understood, because we actually take the second order approximation of the function. So if it was quadratic, the second order approximation was the function itself. So we actually would converge in one step. So like it's not an interesting example. So we take a quadratic function and we added some non-quadratic stuff. And this is an example. The black line is the gradient descent, and the blue line is the Newton method. And as you can see, the black line goes perpendicular to the level set of the function. In every step it goes perpendicular, and it's not the optimal solution, it's not the optimal direction in global sense. And the Newton methods goes like in a straight line into the global minima, so it converges faster. So in general, as I mentioned before, under some assumption, the Newton methods converge quadratically, while the gradient descent converges linearly. Do you want to make a break? Maybe. So, Mira,
yes, let's take a break of 10 minutes, okay? 8 minutes,
yeah,
10 past 10.
10 past 10.
Just pause, not stop, just pause the record.
Yeah. Okay, we're on here. So if you remember, the direction that we got is by 1 second. The direction is we got by taking a quadratic approximation of the function, right? So if you think about it, if you have a quadratic function, so the quadratic approximation of the function will be the function itself, right?
Yes.
So if you minimize over quadratic function, you will get the global minimum because it's a convex function, and you take a derivative and equate to 0, so you get a global minimizer. So
what bad is with that?
It's just that it's not an interesting problem because you converge in one step, right?
Again, so why would you like to converge more steps?
I just wanted to show you a non-trivial example, and if the function was quadratic, it is like trivial example, right?
I think there is a misunderstanding. The idea is that you have a general objective, not a quadratic function. And what Amnon wants to show that when you have a general objective, even if it's convex in this case, it takes time to converge.
Yeah.
That's the idea. And when you have a general objective, when you look at the quadratic approximation, that's what you get. And then you make the direction like in the quadratic approximation. The idea is that you have a general objective, not an easy one, just quadratic, for example.
Yeah, exactly.
Maybe.
Like I can show you a lot of not interesting examples. Like I can take a linear function and then gradient descent also converging one step, right? Or correct.
Cool, thanks.
All right. Okay, so let's continue. So we've seen that the Newton method converge faster. 1 second. So we've seen that the Newton method converge faster, but as we already mentioned in a few words, there is problem with the Newton method. So what is the problem? So the first, excuse me. The first is that the Hessian of the function is very large. So if we have n parameters, the Hessian is n times n, which let's say we have 300 K points and 500 cameras, so the Hessian will be around million by million, which is very large. And as we said, there are three problems. The first is to compute these derivatives. The second is to store it on memory. And the third is to invert it. So naively, we need to compute and store all the second derivatives. But luckily enough, the problem that we are trying to solve is not a general problem, but it's a least square problem. And what is exactly is a least square problem? Is a special case of unconstrained optimization, where our objective function is of the form of sum of residuals, right? And we can write it equivalently by a function from Rn to R, by the decomposition of function from Rn to Rn and from Rn to R. And the last function that we decompose is just the norm, right? So we denote by Rj the jth residual, and R of x is just putting all the residuals inside a vector. So as you can see here, I remind you that the bundle adjustment is also share this property. We have a sum of squares, right? And each term in this case is we can call it a residual. That's it. So it turns out that this problem has a very special structure that we can take advantage of. And just to see how we can take advantage of this, so we will compute derivatives. We'll do it briefly. So the Jacobian of the function R of x, which is a vectorized function, right, from Rn to Rm. So the Jacobian has the form of the gradient of each R. It's just a matrix that each row is a gradient of one residual. So this is for the Jacobian of R. So the gradient of f, just if someone like it's gibberish for him, he can go to the matrix cookbook and verify everything. So the first derivative of f, where f in this form is just the Jacobian times the residual. All right, it's just for deriving the decomposition of functions. Now the second derivative of this function is the first derivative of the gradient, right? And actually what we get is that the second derivative is just composed of two components. The first is the Jacobian transpose the Jacobian that we get from taking derivative of this term, right? It's a multiplication of two functions. So so taking a derivative with respect to the residual, to the R, so we get that that the first term is the Jacobian transpose the Jacobian, and the second term is something which is more complex and depend on the second derivative of each residual. All right. So so how we can use this structure? 1 second. So how we can use this structure? So the Haitian is of this form, as we said. So what we are going to do is to ignore the second term in the sum, the second order information, and just approximate the Haitian by the Jacobian times the Jacobian. Actually, this is called the Gauss-Newton method, which is a very simple modification of the Newton method. That we will see in a minute the advantage of the Newton method, of the Gauss-Newton method. So as I mentioned, the Gauss-Newton can be viewed as a modified Newton method, which is adjusted to the least square problem. The Newton method is general. You can apply to any function that you want. And the Gauss-Newton usually use the structure of the least square problems. So instead of solving the equation that the Haitian equal to the times p equal to the minus of the gradient, we approximate the Haitian but by the J transpose J. And we get a new equation that J transpose J equal times P equal to minus J transpose R, which is the gradient. All right. So in fact, what we earn here is that we don't need to compute any second derivatives, right? The Jacobian, I remind you, which is only the first order. The Jacobian is the first order information, right? It's the first derivative of R. So actually, when we have the first derivative, we can apply the Gauss-Newton method without computing second derivatives and store them. Actually.
Amnon?
Yes.
Can you explain again why did you ignore the residual that we had in the formula?
Yes, I'll say it in one slide. All right, just so. Okay, so I'll say now it's not like something accurate. It's more. It's a kind of let's say heuristic. You can build a counterexample that it's not an optimal choice to neglect the second term, but in practice, but in general, it leads to a distant direction. We will see it in one slide, and in practice, the second term near the minima can be neglected. We will see, and maybe intuition for that.
Maybe you can say that when you are close to the minimum, the residual are small, maybe, and this is the reason that you can neglect the second term. Either small or can be approximated by some linear approximation. Therefore, the second derivative, which is the multiplication there, can be neglected. This is more or less the idea. But you know, it's heuristic.
Yeah. Exactly. So we will say it in 2 slides, but yeah. So for now, we don't need to calculate the second order derivatives, as I mentioned. So so some more aspects about this the Gauss-Newton method, about this technique. So if the Jacobian is full rank, so the J transpose J is strictly positive definite, and it leads to a distant direction. So why is that? Even if we neglect, no matter what the second derivative of the residual, if the Jacobian is full rank, we guarantee to have a distant direction. So why is that? So this is our equation for the update, for the direction. So we solve this, and we actually get that the inner product with the gradient of f is just equal to this thing. And again, because the Jacobian is strictly because the Jacobian is full rank, the J transpose J is strictly positive definite, and we get that because the J transpose J is strictly positive definite, this term is smaller than 0, strictly smaller than 0, which means that we have a descent direction. So this is something that we wanted to verify, that we have a descent direction. So some other aspects of this method. So regarding the question why we neglected the second term, so there are many situations where the J transpose J is the dominate the second term. So for example, we can think about two situations where the residual is close to 0, and the other one is that the residual, the R is close to a linear function. And if it's close to a linear function, the second, the Haitian or the second derivative of R is small, right? And in general, without going into details, the Gauss-Newton algorithm shares the same convergence rate as the Newton method. And that's it. In general, many least square problems follow the behavior in the neighbor of the solution. So it leads to the same convergence. So I described you the method, the direction that we got. So let's see what we earn from the. Well, let's see exactly what we earn from the trick that we saw. So I remind you how we can calculate the J transpose J and the J transpose R. So it's just a sum of the outer product of the gradient of each residual, right? This is the J transpose A, and the J transpose R is just the residual times its gradient, and we sum over all of this. So in general, if you look on this naively, so we get a complexity of n, which is for every sum in the for every term in the sum, we perform n square operation for the outer product, and in the second term we get n times n. But there are two things that we can also take advantage here. So first, in our problem, in the bundle adjustment problem, the gradient of each residual is extraordinarily sparse. Why is that? Because let's say we have a lot of points and a lot of cameras. If we look on this thing as a residual, if only this thing is a residual, so here we have, let's say we are in the projective case, so we have one camera and one 3D point, right? So it sums up to 3 plus 11, which is 14 parameters, right, in the residual. But our problem is defined on R million, or let's say in a very high dimension. So actually what we get is that the gradient of each residual, we have a lot of residual, right, which is n times n, but the gradient of each term contains only a constant non-zero terms, right, which can be used with sparse multiplication or whatever, you know, in order to to perform everything and store and perform everything very fast. Another thing is that if you want to multiply, let's say you're using an iterative method to compute the inverse of the J transpose J. So if you want to compute this multiplication, you can do it even faster than, you don't need to perform all this operation. Why? Because the vector P is in Rn, right? You multiply it with the gradient Rj, which is an operation, and another an operation, right? To multiply it in the vector of the residual, and you do that n times. So to multiply the P with the J transpose J is just n times 2n operation, right? So, and also if we take advantage on the sparsity, so we can do that very efficiently. All right. So this is actually the point that we are discussing this idea, because everything specific for bundle adjustment, everything here can be computed very efficiently.
But we will still have to take the inverse and store. But this is sparse, so the storage is not a problem, right? But the computation,
but the
computation of the inverse is still.
Yeah. So you're right. Computation of the inverse is still expensive, but there are like an iterative methods to compute the inverse. So you can compute it relatively fast. Let's say relatively, but you are correct. It's still it's still hard to compute it. All right. Yeah. So actually, none of the secondary. There are second methods. I think Mira, correct me if I'm wrong, but there are second order methods that knows how to approximate the inverse, but in the second order methods that we will see today, there is no approximation for the inverse.
Something called quasi-Newton that also take something which is positive definite and some iterative way. Do not waste.
So some more nice thing about the Gauss-Newton method. So we can think about it differently, like an equivalent way of thinking about it is just to think that that we don't, like, our function is the norm of the residuals, right? So another way of thinking about the Gauss-Newton method is that we have made a first order approximation of the residual function of the R. And now we want to minimize this first order approximation, and we can verify that if we take a derivative of this thing, we get exactly the Newton method, the Gauss-Newton method. So actually, it's another nice property is like we can think about it as a kind of a mix up between like first order approximation and second order approximation, because we did not make a second order approximation. We did not make a first order approximation of the function, but only for the residual function of the vector function that inside the norm. So just this is just curious. So the last method, the last optimization method that we will discuss is the Levenberg-Marquette algorithm. So in the Gauss-Newton method, we select the scale and the direction such that it leads to a decent direction. In generally, near the minimum, the converges can be relatively fast. However, there are cases where the alpha might be small to zero and almost stuck. And there is, maybe I'll say it, there is another problem in the Gauss-Newton method that, as we showed before, we assume that the Jacobian is full rank in order to show that we get a decent direction. But it's just an assumption that we've made. We probably can get many counterexamples that it doesn't happen. So the idea is to change, to modify the search direction in order to circumvent these problems. So we add like a you can think about it as a regularization parameter to the J transpose J. And we multiply, like instead just taking the J transpose J, we add like some scale, multiply the identity metric. And this is our definition of the new direction. This is the Levenberg Marquette. And to get some intuition, if we take lambda equal to 0, it boils down to the Gauss-Newton method. And if we take a very large lambda, it gives us the gradient descent direction, right? If let's think of lambda, I don't know, tends to infinity or something. So the identity dominates the J transpose J, and then the P can be thought of as gradient descent. So the idea is to some kind of mix up between the gradient descent and the Gauss-Newton method. So as we mentioned, in this case where we don't have to assume that that the J transpose J is strictly positive definite, because if we add a lambda larger than 0 here, it guarantees that this matrix is strictly positive definite. So now without assumption, because we got a positive definite matrix, we guarantee that we have a decent direction. All right, as we did in the two previous methods for the to check the descent direction. So about the Levenberg Marquette algorithm, how to choose this lambda. So a typical heuristic, let's call it, is to initialize the lambda in something that scales like the trace of J transpose J, the average of the diagonal J transpose J times 10 to the minus 3. And then at the kth iteration, if the value P decrease the objective, so in the next iteration we will divide the lambda by 10, and if it doesn't, we will multiply it by 10. So this is the strategy in general. And actually we did not, I did not cover it, but because I didn't want to confuse you too much with a lot of definitions, but the Levenberg Marquette, we use something which is different than line search, which is called trust region, which means that we get an approximation. I will say it in very general because I don't want to get into details, but in general, in trust region methods, instead of looking for the scale, you just assume that in some region, your approximation is correct, and then you change the size of the approximation adjusted to if you get a decrease of the function or you don't have a decrease of the function. And it's a different technique that that can be shown that leads to decreasing in the objective at every iteration. So now someone have a question on anything regarding to the optimization?
Yes, just to clarify, the previous Levenberg-Marquardt method, this is the method to find the direction which we will go. But you just said that this method is a trust region method. It's just a definition, like the class of such methods, and but it does not change the procedure of that you described in the beginning. We're still finding the direction. We choose the step size, and we right or
actually not exactly, but you don't search for the scale. You just minimize the function that this field. You just limit instead of looking for the scale. You can just limit the norm of p to be smaller than some parameter, right? So it's a bit different strategy that I didn't want to go into, but if you limit the norm of the direction, so it's equivalent to decrease the step size, right?
Let me try to say something. Actually, the line search methods start with the direction and then look for step size. The trust region methods assume that the second order approximation is correct in some region, but if it's not true, it shrinks the region. If it's true, it enlarges the region. And actually the shrink and the enlargement are somehow related to the choice of lambda. This is the idea. There is equivalence between the choice of lambda and the region where you assume that the second order approximation is a good approximation to your objective. This is just, in this sense, it's different. This is a trust region method, the region that you trust that your approximation is okay. And this is different than the line search method that you look for direction, you look for a step size. In this notion, it's different. This is two kinds of methods.
Exactly, and the size of the region is like something like equivalent to the step size. Yeah.
Amnon?
Yeah.
When you do the leveling this method, do you check first if J transpose J is inverse or not, and then you decide if to use Gaussian or this one?
Actually, no. In this method, like you need to decide because as we mentioned, it's not a line search. It's a bit different. So you need to decide that you're using this method like before you're using it. Like,
but I can get a better approximation with, let's say, if I know that J this matrix is inverse, so I can calculate it with the first method, with the second method. and then get better approximation, and then use this method for next step, no?
In some cases, I guess you're right. But yeah, in general, like you say, I can check the J transpose J, and then to decide which method to use. You can also check the objective. Yeah, I guess you can do some hybrid strategy, but in general, these are two different methods. Okay. Okay. So let's go back to the bundle adjustment. Now that we know how to optimize the objective with our fancy second order methods. So I remind you that in the objective we have camera matrices. We will discuss the calibrated case. The uncalibrated is simpler than the calibrated. So we will discuss the harder case. So in the calibrated case, we have the camera matrices, which are rotation, rotation and translation, and the 3D point, which are in homogeneous coordinates. And so we can rewrite our objective in this form, which actually we did nothing but multiply the vector in the matrix. So actually, we can H residual here, right? Is H residual here is just in this form, right? And in order to construct the Gauss-Newton or Levenberg-Marquette methods, it will be enough to compute the Jacobian of the residual vectors. So one problem that we need to solve before we are taking the derivatives is how to get a rotation metric. So a rotation in 3D, it has 3 degrees of freedom, right? But if we represent it by a matrix, it's 3 by 3 matrix. So actually, you can think of it as a manifold in R9, right? But when we update, we want to stay on this manifold. We want that every update in our iterative method, the solution will still be a rotation matrix. So we need to find some parameterization of the rotation. So how we do that? So there is someone very smart, which called Rodriguez, which wrote a formula for rotations. So the idea is that every rotation can be represented, if you think about it in a 3D, every rotation can be represented as a direction and an angle that rotates along this direction, right? So a unit vector omega indicated the direction of the axis of the rotation, and the angle theta described the magnitude of the rotation about this axis. So in general, we can write it every rotation as in this formula. This is the Rodriguez formula, where our unit vector is taken, where k is the unit vector, which is taken as a cross product metric, as a skew-symmetric matrix, and we take an exponent of the matrix. So so it's just the Taylor expansion of the regular exponent that you know, and one can verify that This thing actually boils down to be the identity plus sinus of the sine of the angle times k plus 1 minus cosine of the angle times k squared. And why is that? It's just because when we power this matrix, when we get the power of this matrix, it just sums up to be either skew-symmetric or symmetric matrix, and it will be the same matrix with scale. Just you can write it down, and it's not very hard to see.
Can you please explain why the rotation matrix is the exponent of theta times k?
Actually, I don't have a good intuition for that. It's just the formula. What is it? Mirav, do you have any intuition for that? I'm not sure.
Yoni, can you help us?
No.
Intuition for what?
For why is the rotation is the exponent of this thing, of the from the Rodriguez formula for the rotation with the axis and the angle.
You can. Do you mean geometric intuition?
Yeah.
Yes, there is a drawing in Wikipedia that you can see that explain this notation. Why this is the conversion from the line axis to the rotation matrix.
Okay.
Yes, it's actually very geometric. You can look at the. You need to see the axis and the angle and the arrows, and I think that it's very clear when you see the figure.
All right. Okay, so I'll continue. Okay, so actually, what we'll do in what we'll do next is to just given an initial rotation r0, we will neglect the quadratic term that we have seen before, and just keep the first term that we've seen. So actually we can write it, right? We had this term, so we can write it as identity plus the skew-symmetric matrix, which the skew-symmetric matrix has only 3 parameters, right? Because it's skew-symmetric. So we can take a trivial basis to the skew-symmetric matrix space and just write it as identity plus a linear combination of this skew-symmetric. And the thing is that when I multiply it by R, I guarantee that I have again a rotation. Right? So now we compute the derivatives of this thing. Actually, it's not very important. You can take a look afterwards about the exact form of the derivatives. But in general, if these are residual, we need to calculate the partial derivatives of each residual with respect to A1, A2, and A3, which are the rotation parameters, our rotation parameters, and T1, T2, T3, which are the location parameters, and the entries of the 3D points, right? And this thing we need to do at every, we need to approximating the current parameter and in every iteration. So if we assume we have n cameras and m scene points and that all the points are visible in all the cameras, so actually we have, as we discussed, 6n times 3n variables, and the vector that we discussed of the residuals is just equal to the m times n, right? Because every point is visible in every frame. This is our assumption. And that Jacobian is of size m times n times 6n plus 3n. All right, so actually we're close to the end. This is just to see like what is the final result of the bundle adjustment. As you can see, for example, here we have 341 cameras with 133k points, and this is the structure you get after all the optimizations. And another example is 415 cameras and 161k points.
No?
Yeah.
Can you go back to the slide before the results, where you showed the one before? Yes. So here you just showed the parameterization of the rotation matrix, just so we can calculate the Jacobian, and after that we apply that Levenberg-Marquardt method, and we are done.
Mm-hmm.
Okay.
This is the question. Yeah. So yeah. So actually, once you have the Jacobian, for the Jacobian, you need only the first derivatives, right? The Jacobian is only the derivatives of the jth residual with respect to the ith parameter. So once we have this Jacobian, we plug it into the optimization methods that we discussed. In practice, most of the bundle adjustment packages that exist today, actually, if you need to do this in practice, there are many efficient packages that you can use that perform this. You might want to implement it by yourself, but in general, there are packages that do it, and they usually use Levenberg-Marquardt to optimize it. You can choose the other algorithms that we've seen, like Gauss-Newton, for example, to optimize the objective. And once you optimize the objective, you get this thing. So how do you, this is only a drawing of the 3D point, right? It's not, you can think of it as a 3D, like it's animation of a 3D plot where each point is a 2D projection, is a 3D point, and the camera's location is just generated from the camera location, and the angle of the green shape, I don't know, is from the rotation, right?
Amnon?
Yes.
In the previous slide, when you calculate the derivatives, you are taking an example only for the x case, right?
Only for the xk?
X case, because this is so R1 equal to X minus.
Yeah.
So we have also for the Y, right?
Yeah, correct.
So how do you merge them together again?
So actually, you can look on it. You can look at it at the different,
Residual. It's another residual.
Yeah.
Just another residual. For each component in the summation, you have two residuals, one for the X and one for the Y.
And one question: how did you find that the size of the Jacobian is 6n plus 3m?
Because it's the number. Let's think about it. When you have residuals, actually, this should be 2 times mn, but if you already catch it. So if you have a function from Rn to Rn, right, where n is 6n times 3m, we've seen because 6n is the number of parameters in the 6 is the number of parameters in the camera times n, and 3m, like 3 is the number of parameters in each 3D point times the number of points. Right?
Okay, so in the Jacobian I just put 2 before mn.
In the no, actually, it depends how you write it. But if you write it here, I wrote it as a different residuals, right? So so it should be 2mn, right? Because every 3D point and camera generate 2 residuals. But it's I'll fix it for the when we publish the.
Thank you.
Okay. So just to sum up, so the bundle adjustment is a nonlinear refinement for the structure for motion problem. As we mentioned, it's not a direct solver because it's not convex and it needs very good initialization. So usually we'll solve it using Levenberg-Marquette algorithm. The packages that exist today solve it with Levenberg-Marquette, and it's improved the solution by a lot. If some of you will, let's say, do some real application of structure for motion, he will must use bundle adjustment to refine the solution. Otherwise, the solution is not accurate enough. And